All right, I think we'll get started and people will join. Welcome everybody to this innovation showcase summer series entitled HydroSphereAI, Machine Learning Driven Hydrological Forecasting in a Changing Climate, presented by the Ontario Water Consortium in collaboration with Aquanty. And I'd like to start to speak a little bit about the Ontario Water Consortium. The Ontario Water Consortium is Ontario's only sector-supported organization dedicated solely to water innovation. We bring together researchers, companies, municipalities, and governments to drive collaborative R&D, pilot testing, and real-world technology adoption. We help bridge the gap between research and market-ready innovation. And while there are many innovation organizations across Canada, none are focused specifically and exclusively on water, like OWC is. OWC's collaborative model delivers measurable results. Over the past decade, we've helped mobilize $90 million in project funding, supported or created more than 350 industry jobs, and advanced nearly 80 water technology projects. We've partnered with more than 100 academic researchers and helped build infrastructure, including wastewater test beds in London and Guelph. We do this by connecting innovators with adopters and aligning the right funding, partnerships, and support to move solutions forward. Before introducing today's webinar, we also hope you'll join us again for the rest of the webinar series. On July 7th, we'll hear from Dynamita, showcasing powerful modeling tools for wastewater systems and resource recovery. And then on July 14th, Bishop Water will present on decentralized low energy solutions for managing biosolids and nutrients, ideal for small and rural communities. I will drop the registration link for those in the chat in just a moment. And of course, all sessions are free to join. I am now very pleased to hand it over to Dr. Andre Erler, who's a senior climate scientist at Aquanty, to begin today's webinar entitled HydroSphereAI, Machine Learning Driven Hydrological Forecasting in a Changing Climate. The development of this technology was supported by the Ontario Water Consortium's Water Industry Growth Program, which concluded in the spring of 2024. And with that, Andre, the floor is yours.
Okay, thank you. And do I have to share my screen again?
Yes, I'm just stopping my sharing and you should be able to go ahead.
Okay. All right, can you see my screen now?
Yes, we can.
Okay, excellent. Then I will start. Okay, yeah, so like Robert said, I'll be talking about HydroSphereAI, our machine learning-based streamflow forecasting system that we've developed with funding from OWC. And before I get into sort of the technical aspects of HydroSphereAI, I will talk a bit about Aquanty and our background and how we got into this. And then at the end, I will also go over our real-time web platform where we are serving our forecast, the graphical user interface, and then also the infrastructure that underpins all of this, because it's actually very important and I don't want to minimize that aspect. So even though the main part of the talk is, of course, focused on the machine learning models. Okay, so Aquanty was founded as a research spin-off company from the University of Waterloo. And initially, our main focus was on numerical modeling, and specifically numerical modeling of surface water and groundwater interaction. So our flagship product at the time, and actually still, is HydroGeosphere. That's a fully integrated surface water and groundwater model and numerical model. And initially, we did primarily consulting type work where we applied HydroGeosphere in various contexts. But since then, we've also broadened our interests and our activities. And in particular, we started to get into real-time forecasting or operational forecasting. And that is under the umbrella of our hydro-climatic platform. And HGS-based, physics-based real-time forecasting is still part of that as HGSRT. We also have modeling on demand that runs in the cloud as soil moisture forecasts. We also host a lot of just data sets on our platform through the Canada One Water initiative that I'll also mention a bit more later. And then, of course, HydroSphereAI is part now of our forecasting platform of hydro-climatic. And we've done a lot of research over our careers. Aquanty staff are usually academics, at least in part. Most of our senior staff is actually adjunct at the University of Waterloo, including myself. We continue to publish, and we have published on many topics related to hydrology and climate change. And so that ranges from climate change at the watershed scale to climate change impact at the continental scale. And that's, of course, what I am also involved with as well, since my background is in climate science. But other colleagues do mine site high-resolution modeling or mountainous catchments or even agricultural catchments with tile drains. So very detailed at times. But also water quality and contaminant transport, even up to coastal aquifer systems. So a lot of different things that we do in Aquanty. And we've kind of put a lot of this together in our real-time platform to serve it more as an actionable insights to stakeholders and to have more of an impact rather than just publishing academic papers. And so with this, we can say Aquanty basically has three major pillars. And so one of them is HydroGeosphere, still is, and that really underpins all of our consulting work and all the work we do in the oil sands, also for the nuclear industry. But then there's also Canada One Water, and that's an open source initiative that we started with the Geological Survey of Canada to essentially assemble large-scale data sets for hydrological modeling and make them available. And we use these data sets very extensively ourselves, and that does not only include climate and hydrometric data, but also a lot of geological data and land cover data. And this project and the data sets resulting from it have really proven invaluable to the development of HydroSphereAI as well. Yes, and then there is, of course, hydro-climatic, our real-time forecasting business, which HydroSphereAI is part of. And we've actually been doing this for quite a while. We've actually been running hydrological forecasts since 2018. It started in the South Nation watershed with South Nation conservation. But we've expanded and deployed real-time forecasting platforms in many parts of Canada at this point and have been operating those for quite a while. And recently, we've even deployed one in Barbados, which is quite interesting. But now to HydroSphereAI specifically. And before I get into the technical details, I just want to give a very high-level overview of what this is. It's essentially machine learning-based streamflow forecasts or streamflow simulations that can be done in a forecasting or also in a historical reanalysis context. And these models are based on the LSTM architecture. So this is a common way for time series modeling, and they are forced by weather data. And then, of course, can be fine-tuned for specific regions, or we can also train them for specific forecast endpoints. So streamflow is, of course, the most important one, but also snow, for example. We have very wide coverage, basically all of North America, with the data sets that we have from Canada One Water. So we can essentially deploy forecasts anywhere in North America very easily. And we can also extend this to other regions, not just North America, without too much effort. And one interesting aspect of these models is also that they're fairly good at predicting in ungauged basins. So with these forecasts, we are not actually tied to Water Survey of Canada or USGS gauging stations. We can forecast at any point on a river. But when we do forecasts, as opposed to historical reanalysis, we actually force those models with weather forecasts, so numerical weather forecasts typically, but can also be AI-based weather forecasts, which are actually very good at this point. And this can be over time horizons of a few days or even less than a day to seasonal timescales. And then we have a web platform where we serve those forecasts in a graphical user interface, but we also have APIs, and this is, of course, all automated. So this is a very high-level overview of the system. But of course, I also want to point out that using machine learning for hydrological forecasting or modeling is not an entirely new idea. People have been trying to do this for the better part of 20 years now. And initially, it was really just like feed-forward perceptron neural networks or random forests that were attempted to be trained like a rainfall runoff model. And this was generally not very successful. And essentially, so the intuitive explanation for this is that in a single watershed, there's not enough data available to really constrain a complex model. But at the same time, the processes are too complex to be learned just from the data that's available from one watershed. So if you have a simple model, then you can constrain the parameters, but the forecasts are just not going to be very good. Whereas if you have a very complex model, you could in principle model the behavior, but it will just overfit. And either way, you don't end up with good predictive skill. And this problem was really overcome or solved in 2018 by Frederik Kratzert. And this is the 2018 paper is really a seminal paper in a hydrological prediction with machine learning. And Kratzert essentially had two significant innovations that really made this approach viable. And one was the use of LSTMs. So the rough architecture is shown here. The key aspect of an LSTM is that it has a memory cell. And so it has an internal state similar to a physical model. And then the other one was that Kratzert et al. Trained these LSTM models on a very large set of watersheds, not just on a single watershed. And that really made a huge difference in terms of being able to constrain the parameters in the model. And that was enabled with the availability of the CAMELS dataset. And so this is now relatively established in academia, and there's still research going on with different model architectures, different loss functions to an extent. A large focus now is on the interpretability or explainability of these models in academia. But academia, of course, does not deploy these models in an operational context. And as you will see later in this talk, there's a lot that goes into that operational deployment that goes well beyond what can be done in academia. Now I want to briefly talk about these two aspects, the LSTM architecture as well as the data sets, because they're really the key aspects here. And so LSTMs have, in addition to just the model weights that you typically have in a neural network, a memory cell. So they're recursive, they're recurrent models, not recursive, but with a modification where the memory cell is actually additive, which solves the vanishing gradient problem. So it's an architecture that can maintain very long memory over a long time, much more so than regular recurrent neural networks. This makes them in many ways very similar to rainfall runoff models, and they can be thought of as a drop-in replacement for rainfall runoff models in the functional sense. In that you have weather data that's coming in and then streamflow data that's coming out, and an internal state that describes the current state of the watershed. And with this state of the watershed, what I mean are things like snowpack and groundwater table, antecedent moisture conditions, So this can be interpreted physically, although it is not explicitly physical. The model learns the physics from the data, right? It's not handcrafted like in a conceptual model. But this also means that these models need to be spun up in a very similar way as a physical model. And so typically about a year of spin up is at least necessary, so that the model has gone through one complete seasonal cycle and has a chance to build up the snowpack, for example, in winter. As a side note, LSTMs actually come from natural language processing, but they're used primarily for time series prediction at this point, because in natural language processing they've been replaced by transformers. But you could think of these LSTMs as maybe a very early ancestor of ChatGPT, although the difference is now quite large. And in fact, transformer models can also be used for time series prediction and also for hydrological prediction. Now to the training data set. And as very often happened in machine learning, really the availability of large standardized data sets really spurred progress in machine learning and made really the decisive difference. And that was really the case here too. First, there was the camels data set, which is US only, and that figure is from camels. And then relatively quickly after that came HISETs, which included Canada and parts of Mexico, so then North America. And this camels or HISETs data set essentially includes dynamic forcing variables, so weather data, as well as geographic or geological attributes like land cover or topography and slope, but all averaged over watersheds. And this is important. So the data that goes into these LSTM models is always averaged over a watershed or a HRU, if you will. So they're essentially HRU models, hydrological response unit models. So small areas that can be assumed to be relatively homogeneous. And so Kratzer et al. Used the camels data set, and then there were subsequent papers using the HISETs and caravan data sets. But we've actually assembled our own data set using the outputs from the Canada One Water project. And so that includes weather data, so the weather data are actually from ESMWF, Ag-Arrow5, and then also from ECCC, the Kappa data set. But then the geographic data are primarily from Canada One Water. And then, of course, the gauge data is from HIDAT. And so we've significantly increased the size of the training data set and also improved the quality of the training data set, because that was really the main problem with the extension to Canada, that it relied very heavily on just Arrow5, and the addition of Kappa has significantly improved it, as I'll show later. All right, and so Canada One Water was really important in this entire endeavor to get the static data across North America. Now, before I'll talk about the validation and the skill of the models, I do want to make sure that we are all really on the same page in what these models do and what goes in and out of these models, right? So there are LSTM models, and then a significant part of the data that goes into a model are the catchment attributes. So when we are running a forecast for a catchment, we have to give the model the static data about this catchment. So the elevation, slope, land cover types, forest cover, for example, also soil types, but then also the general climate. So the annual maximum temperature, annual minimum temperature, and annual precipitation totals, that also goes into these static attributes, and that's computed from a reanalysis. And then there's dynamic weather data that goes into the models. And depending on whether we're doing a historical simulation or a forecast, these are actually different, right? And then what comes out of the model is a time series of stream flow, or also other variables that we can add, but primarily stream flow. And so on the left-hand side on this graph here, you see the red line. This is a historical simulation. So it's a spin-up. And this is forced with observed weather. It generates a streamflow time series for the observed time period. So it's kind of like a reanalysis. And then you can see in the background, there's also the actually observed streamflow. And then where this now dashed line is, this is where we are initializing a forecast, and then we are running those models with weather data from a numerical weather forecast. And this is an ensemble forecast here. So the red line represents the median, and then the green shading represents the ensemble spread, right? And there are dots here, and those are daily. And the reason for this is that this is a daily model. I will mostly talk about daily models. So they make predictions in daily time steps, and they're predicting daily averages. We also have short-range models that predict hourly, but most of the time I'll be talking about the daily models in this presentation. So you have static attributes as well as catchment average weather data going into the models, and then streamflow time series comes out of the models, and they can be forced with historical data or with a weather forecast. Okay, so keep that in mind, and I'll show a couple of those graphs later. All right, now to the validation. The way that we train the models is that we train on essentially all catchments in North America or in northern North America, typically when we're deploying models in Canada. So this encompasses many different climate zones and just a lot of data. So typically about 1,000 watersheds or catchments would be involved there. And we're training over a historical time period, typically 1980 to 2020. And we evaluate this with fourfold cross-validation. So we're training over 30 years and then withholding 10 years, and then evaluating over the 10 years. We do this 4 times so that we cover the entire time period for evaluation. And so if we do this, we can summarize the test results in a graph like this. So this is the Nash-Sutcliffe efficiency, a common skill score, NSE, on the x-axis, and so 1 is perfect skill and 0 is essentially no skill. And then the CDF is shown here, so the cumulative distribution function of the number of models or catchments that, the number of catchments where we exceed a given skill. And this is in percent, so or relative, right? So, and then we have a median NSE where the median lies. And when we do this, when we do basically training and test evaluation just split by time, so this means that the models have previously seen the watershed that they evaluated on, but they're just predicting for a different time period, so they haven't seen the weather. Then we get a skill of 0.73, so this is pretty good for any hydrological model. But it is not specifically fine-tuned for any particular watershed. So this is then, we train this with Ag Era 5 data, and we use our Canada 1 water static attributes and gauge data from HYDAT for the daily models. Then we can also split the training test scheme differently. We can train on a subset of watersheds and then evaluate on another subset of watersheds and then do cross-validation again. So when we do that, we effectively get a prediction in ungauged basins, because then the models are always predicting in basins that they have never seen before. And that is what the green dash line here is. And that gives us still a skill of 0.66. So that is actually a pretty good skill for ungauged basin prediction. We're quite happy with that. And this really means we can do a useful ungauged basin prediction, or prediction in ungauged basins. But skill in gauged basins, meaning where the model has seen the basin before, is of course better, even if it is not directly calibrated or specifically fine-tuned for that basin. Okay. Now, something else we can do is data assimilation, or as we call it in machine learning, data integration. But it is, you can think of it in a similar way as data assimilation in physical models. And so here the models during their spin-up period will see the previous day's stream flow, and then can basically correct their prediction based on the recent stream flow. But we typically also have about a 50% holdout for this, so the models don't see the stream flow all the time. But it significantly increases the skill again, largely because the models can then start correcting biases for specific basins. And so when we do this, we get a skill of 0.84, so very high. And we call these QLSTMs, so Q for the observed stream flow, and so they integrate the observations. And these are actually the models that we primarily deploy, because it does increase the skill notably, especially or in the spin-up period. In the forecast period, of course, it doesn't, but just having a better spin-up will increase your forecast as well. Okay, so the distribution of skill across the country, and this is just showing Canada here for the QLSTMs, but we can actually do this for other regions as well, including the US. There is a pattern to the skill distribution. It's not homogeneous, and we have the highest skill where we have the dark green, typically in snow-dominated catchments, especially in alpine areas or in northern Quebec and also in northern Ontario. There we have really good skill, and generally in northern Canada we do have pretty good skill. But in southern Ontario, for example, we don't have that good skill. So for comparison, in snow-dominated watersheds, we often have, it exceeds 0.8, you often 0.9. Whereas in Ontario, it's typically something more like 0.6. So it's not that good. And the reason for this is primarily, I think, that we have a lot of human interference and a lot of changes over time. So for example, tile drains have been deployed and we don't normally know when or where. And then there's also just direct human interference through flow regulation, dams, right? Which make it difficult to really learn the underlying behavior for the models. And yeah. And then the worst region is actually the prairies, and this is the case for most hydrological models. So here we often have a skill below 0.5 degrees NSE. And here, a large problem here is potholes and the distribution of potholes, which is often not known, and then large areas in basins that may not even contribute any runoff. And this is difficult to handle for the machine learning models. So this is something we are still actively working on. But I would also point out here that in many areas in the prairies, the runoff that is generated in the prairie catchments is actually very small and almost inconsequential. And most of the stream flow that is relevant in these areas is actually stream flow that is generated in the alpine headwater regions, where we do have very good skill. So this is actually a silver lining here. For the larger streams, you would have better skill. All right, and so now one more thing that we can add on top that further enhances skill, and that is training with kappa instead of error 5. Precipitation in kappa actually, it's in error 5, actually does have some issues, and often the timing is a bit wrong. It has biases as well, quite notably. And using kappa for precipitation actually really helps improve the skill in training, just because the precipitation timing is better and the distribution is better as well, especially in summer. So yeah, and that bumps our skill up to actually 0.88, so almost 0.9. That's something we can be quite happy with. So putting this all together, the features that we currently offer for HydroSphereAI is augmented data sets, of course, beyond what is available in the academic literature, and we can also do fine-tuning for specific applications. And because we can do really good forecasts in ungauged basins, we can also create synthetic gauges. So we are not tied to any WSC or USGS stream gauges. We can just drop a pin anywhere along a river and then compute the upstream contributing area and generate our data, static data sets, and make an ungauged prediction that actually does have some skill, even though it's of course hard to evaluate that. And then I've already presented the data integration, which significantly improves our spin-up, which then of course also improves forecasts. And something else that we've been thinking about is integration of rain gauges in order to further improve the spin-up for regions where we do have rain gauges, which is of course not everywhere. What we are also offering is snowpack forecasts. So these are models that are specifically trained to not only predict streamflow, but also snowpack. And this actually works really well. So we're getting very high skill with snowpack. And we also have a soil moisture prediction, as well as, of course, streamflow prediction. So these are, and we could also develop additional endpoints here. And then finally, I've mentioned that we do not only have daily models, but also hourly models. Those are, of course, primarily relevant for flood forecasting. And we've just deployed those in a preview in our beta test that I'll mention later. But those are operational now. And we also have high and low flow alerts for those. But we also have subseasonal forecasts, and we're also working on seasonal forecasts. So a range of different time horizons for different applications, ranging from flood to drought. Good. Now let's look at some examples of what this streamflow prediction actually looks like. And so now I'm just showing some streamflow simulations from our models for historical scenarios, right? So test results, if you will. And in the top panel, you see streamflow. And in the bottom panel, you see snow. So this is a model that predicts both streamflow and snow. And blue is observations. And orange or yellowish color is the model simulation. And so this is forced with historical data. And the blue shading shows the standard deviation range of the historical climatology, essentially, of the historical variability, so that you can sort of see what the range of variability in this region is. And this is an example for an alpine headwater catchment in the Banff Jasper area. I think it's a headwater of the North Saskatchewan River. And there is a flow peak in spring with the spring freshet, but then also very high flows in summer that is partially snowmelt, but also partly convective precipitation in the mountains. And then, of course, in winter, everything is frozen. And yeah, you can see that the streamflow simulation is pretty good, and the snow simulation is actually even better. To a large extent, because snow is just easier to predict because it is an integrated quantity, so there's a lot more smoothing and averaging going on with snow than with streamflow. And so snow accumulation takes place until about the end of April, and then in May and in June it starts melting and generates runoff, right? And this is, of course, an area where our models perform relatively well. This is an example in Quebec. And here the behavior is a little bit different. So there's a very pronounced spring freshet. And then there is also some runoff in fall, which is mainly from rain events in fall. But then, of course, also snow accumulation, but it melts a bit earlier. So it starts melting already in April. And then by mid-May, it's all gone. Here, the snow skill is still quite good. The skill in streamflow is not quite as good. This is to some extent because the weather data sometimes overestimates or underestimates events or misses events, and then of course the forecast will also not be correct. And this is with error 5 forcing. So there's some limitations to the forcing data. Okay, then these are daily models. We also have hourly models for short-range forecast. And the way that those work is that they're actually multi-timescale models, or essentially two models. There's a daily model and then there's an hourly model. And we have to initialize or launch the hourly model from the daily model. We still need the daily model because we do need this long spin up that is actually not really feasible to run with an hourly model. But yeah, we need to build up the snowpack and the antecedent soil conditions for the hydrological forecast to make any sense, right? But then we can launch the hourly model from there. And with those, we're also getting an open loop skill, meaning with no data integration, of about 0.7. And so this is a schematic of how this works. Whereas here on the left-hand side, this is a simulation from the daily model over 2 spring freshet seasons, so one here and here's another one. In Northern Ontario, so this is also one where we do have pretty good skill. And then when we zoom in on the second freshet, like here, then we can see a higher resolution prediction where we're actually resolving a lot of the ups and downs better than with the daily models. One other thing I can highlight here, and this kind of speaks to the limitation of forecasting. So even though this was actually done with Kappa, sometimes there are some precipitation events that get missed. And so here in summer, there were probably convective events that generated runoff that were missed by the models or underestimated, often because they're underestimated in the forcing data. And so this kind of speaks to the utility of integrating in situ rain gauges for specific areas where there may not be direct observations. So in Northern Ontario, Kappa is actually to a large extent model background. Right? All right, and so when the weather data or the forecast is wrong, there's not that much we can do. Good. So now I want to talk a bit more about sort of deployment questions and how this looks like in operations. And so we are currently running a demo or preview forecast watershed that you can actually see when you sign up for our platform. You immediately get this. They're randomly distributed stations across Canada where we are running forecasts. And this is not very expensive to do. The models scale quite well. So we can do this for thousands of catchments. We actually have US coverage as well now, but the demo here is just for Canada. It's running with our Canada One water data sets. And then for weather forecasting, we use primarily ECCC products. So for the spin-up, we use Kappa, but then for forecasting, we use for short-range HRDPS, and then for medium-range forecasting, JEPS, so the Global Ensemble Prediction System. But one caveat that I have to mention is that these models only predict for catchment sizes that are smaller than about 2,000 square kilometers. So this is kind of this HRU approach, right? But of course, there are many large rivers that are of great interest in Canada, and especially for hydropower, for example, but also other applications. And some of those rivers are really very large. And these are some of the major river basins, so Mackenzie, Nelson, and St. Lawrence. These are really large rivers. And we cannot predict those directly with the ML models. And the reason for this is that they're essentially like rainfall runoff models in that they simulate the runoff generation process, infiltration and evapotranspiration and snow accumulation and melt, but they don't simulate or account for routing delays. So whenever routing or streamflow routing in a watershed becomes significant, which tends to happen at a larger size, then the predictions will not be very good. And also in cases where there is a significant degree of inhomogeneity across the catchment, then the forecast will also have problems. And so like an HRU-based rainfall runoff model. But this is actually not a fundamental problem. And we don't even need to reinvent the wheel here and come up with some fancy machine learning algorithm to simulate large streams, because routing is actually a pretty well-established technique. So there are routing models that essentially work with channel flow dynamics that work really well, and they're pretty fast. So this is not something that requires a new model. And we can simply take an existing routing model and connect these HRU-based rainfall runoff models and then route the water into larger streams. And the one advantage of this is that we can actually also handle flow regulation in the routing component, and which is difficult to handle in the machine learning component. Right? And so here's an example where we've done this, where we've deployed a routing model, and this is part of the Peace River, the Smoky River, and that's a tributary. And we've set up a routing scheme up to the Vatino station. So on the left map here, you can see a complete but non-overlapping delineation into HRUs or subcatchments. And each of these subcatchments runs an ML model. And then there is a routing scheme that is sort of shown in blue here that connects all of these HRUs into a stream network and then predicts the stream flow at various locations and also the outflow, which is here. And so on the right-hand side is the hydrograph at this outflow site for the test period. So this has not been calibrated extensively. This is almost out-of-the-box performance. And over the test periods, we get an NSC of almost 0.8. So this works really well. But this is, of course, also an area where our ML models perform quite well, too, because these are snow-dominated alpine catchments mostly. But yeah, so this is how we can handle large rivers with our ML models. But we do need to set up this routing model, which we kind of need to do specifically for specific applications. So this is something where we'd have to set up a watershed for you. This is not something we have in our free ML Canada-wide demonstration watershed. And before I move on to the platform, I actually do want to highlight some points here for hydropower specifically that do relate to routing implementation as well. And so if you're a hydropower operator, there are essentially two main benefits that our forecasting system can offer for you. And one is actually not even forecasting, but more current state estimation. So this system can actually be used as a form of a digital twin. So imagine you have a large catchment area with many large remote areas where you don't have very good monitoring, but you're getting inflows from that area into your reservoir, for example. We can run the ML models with a routing component using remote sensing-based forcing or reanalysis forcing, and estimate relatively well what the runoff generation and the flow generation in remote areas is, and then what your through the routing system, what your inflow is going to be just from observed precipitation and the estimated melt and runoff generation, and then the delay through the routing network. And if there are monitoring stations, be it rain gauges or streamflow gauges, we can also integrate this with our QLSTMs and then actually make very good educated guesses about what's going on in the entire upstream area of your reservoir. So this digital twin function is actually not to be underestimated. It can work really well if you don't have very good monitoring set up. And then, of course, there's also forecasting. So HydroSphereAI is primarily a forecasting system. So we can run medium range or even seasonal forecasts that project the expected precipitation and then resulting runoff generation and inflows out over days or even weeks. And this can help you plan different operation scenarios, for example. And those scenarios could even be run through the routing component. Right. And so this really means you can optimize the generation efficiency much better and reduce costs effectively and minimize unwanted spill events. And at the same time, you can also mitigate risks by planning ahead for extreme weather events, and it would probably also help with regulatory compliance. And so I would suggest to consider this for hydropower applications, because I think there are significant benefits. And with that, I want to spend the rest of the presentation on our actual forecasting platform, which we have developed essentially to make all of this science and forecasting available to end users. And there are different components to this. And of course, there is the external component where we're pulling in data from government agencies like ECCC or direct monitoring data. And then first, I'll talk about the user interface component where we have APIs as well as graphical user interfaces where we serve analytics and actionable insights from these forecasts. But then there's also a very large part that's essentially the infrastructure, and I want to talk about this a bit as well. And because there's a lot more than just the ML models that goes into a forecasting system. So there is, of course, computing and the infrastructure. There's databases and there are other numerical models and a lot of simply data pipelining. But before I show you the forecasting platform and talk about this, I also want to mention that we are running a beta test of HydroSphereAI with Conservation Ontario at the moment. And this is in Ontario for all 36 conservation authorities in Ontario, where we are running at all OWC gauging stations that have catchment areas smaller than 2,000 square kilometers. And there are almost 20 CAs that are actually quite active and participate and use the forecast or evaluate them. And at this point, if there's anybody from the CAs here, great thank you for your feedback. This has been incredibly helpful for us to improve the system, and we are continuously improving as well. So having this opportunity to run the beta test and getting feedback from actual users has been absolutely invaluable and a great opportunity for us. The forecasts we have deployed here are 16-day daily forecasts based on the Global Ensemble Prediction System from Environment Canada. And then recently we've deployed 2-day hourly forecasts based on the high-resolution deterministic prediction system. But those are fairly new. And there is a difference between those two in that the HRDPS predictions are deterministic, so they don't have an uncertainty funnel, as you've seen before in the graphs. That's for the ensemble forecast. Okay. Now let's look at what the platform looks like. So this is a screenshot from some time earlier in the year when there was still snow. And I'm primarily showing this one here because it does show the snow dust layer, which is quite popular here in the background. And this is to highlight that we do have a lot of data layers in the platform as well on top of our hydrological predictions. And also precipitation, for example, Kappa, and also current radar and various satellite products. But so when you look at a watershed view for your particular watershed, then you'll see something like this with the outline of the watershed, and then balloons at all the locations where we are offering forecast time series. And most of these will be WC gauging stations, but upon request, we can also put in custom synthetic gauges at any point along a stream where you can get a forecast, but then there will, of course, not be any observations for that. So if you click on one of those, you get a forecast graph that looks about like this. And this is very similar to what I've shown before at the beginning of the presentation. So you have the spin-up period here shown together with the observations. Is in fact the same graph that I've shown before. And then there is a marker for when the forecast was initialized. And then you see the forecast period, which has this ensemble funnel that indicates the uncertainty. And then you also have dots that mark each day of the forecast. So this is a daily forecast. And over 16 days. So, and for the short range forecast, you would see this hourly and you would not see the uncertainty funnel. Good. Now, I want to show a brief example of what these forecasts look in action. At the end of March, there was a storm that rolled through southern Ontario, and we were running forecasts for that. And so here I'm showing forecasts for a number of different gauges that are also marked here. And then the map view here also shows the kappa precipitation. So precipitation from the kappa product that fell for each day. And you can see that the forecasts kind of march forward. The black line are the observations, and then we have different initialization time points. So this is about a week out, and then we're just moving closer into the event. And so I just want to show you this station here in a close-up, and that's here. That's Stingman Creek. That's near London, in the Upper Thames watershed. So this is basically the same graph that you've seen on the animated slide right now. These are the 5-year, so the 2-year and 5-year flood levels. And so about a week out, the forecast is pretty uncertain. And the uncertainty is relatively large, but the actually occurring flows were pretty much within the uncertainty. It shows a relatively smooth increase and then decrease. The main reason for this is actually that this is an ensemble forecast, and there's just uncertainty about the timing of the events. And what we're seeing here is the median, right? So it is not the case that most of these forecasts just predict a smooth increase and then decrease. What is actually the case is that there are multiple forecasts that all predict the peak at a different time. And that's why it ends up looking like this. And then you can see that there are a lot of peaks here, but they are in this area, but they are they occur at different times, right? Okay, so if I march this a little bit forward, then as we are still further out, there's a lot of uncertainty. But then when we are moving in, the uncertainty funnel actually narrows, and we still see that the actual flow is still within roughly the uncertainty. But the forecast becomes sharper. And so now that we are 3 or 4 days out, it's actually fairly accurate in the forecast. And the uncertainty has also narrowed. And the timing now is actually quite good. So when we see a when we see a plateau like this, this is often associated with an event that crosses 2 days, and these are daily averages. And so then we have a high flow average on 2 days, but it's lower. Whereas in the forecast mostly place the event a little bit earlier, and then it would just be in 1 day and would be higher, right? And so when we then go closer into the forecast, then it becomes more and more certain. The uncertainty decreases, and now it's fairly sharp, right? So this is essentially how the ensemble forecasts work. Okay, good. And so this is an example of these forecasts, but what goes into these forecasts? And now the last 5 or 10 minutes, I want to talk a bit about the infrastructure, even though it is not as sexy. But there was really a lot of work that went into this. And specifically for forecasting, we actually, and I've highlighted this a couple of times, we do need to spin up the models for about a year, right? So we need to actually assemble a spin-up data set in real time that goes up to today and back about a year that we can run the models with, and then we transition the models into a forecast. And so the spin-up period is the red, and then the dotted line is where we initialize the forecast, and then we get to the forecast, and there's the forecast funnel with uncertainty again. And so this is for the JEPS forecast. The spin-up is with HIDPA, that's kappa, right? And of course, data integration can significantly increase the spin-up. And so this is a case where we don't have data integration. And so there's significant deviation, right? Okay, and so if we put this all together with what I've talked about with model training and skill evaluation before, this actually means we have 3 climate data sets that we are using here, and that are all sort of operating on different timescales. And the first one is the historical weather that we use for training and evaluation of the ML models. And this is usually what's used in academia. And that's relatively easy to get. You can use reanalyses or monolithic climate data sets. There are a number of data sets around. And then there are, of course, also at the very end, the forecasts. And this is typically what you think of when you think of forecast. We need to force with a numerical weather forecast, or also with an AI-based weather forecast, right? But then there is this really important part in the middle, which is the spin-up, the near real-time weather data. And this is really important, but this is actually technically quite difficult to do, because we need to assemble these data essentially ourselves and archive it ourselves. And so that's often the part that's kind of missing when you're trying to operationalize something. And so this, of course, all has to run automatically with automated workflows. So we have to download the data. We have to do a lot of data transformation on it. And then we also need to archive and store the data and push it to a database so that the API and our web platform can access it. Right? So this actually involves a lot of infrastructure. And in particular, the weather data processing is quite involved. And that's probably from at least equal, if not more work than the machine learning training. And of course, we already had a lot of this because we were already running physical model predictions, which also require all of this infrastructure. And so the weather data involves downloading gridded binary files from Environment Canada and then reprojecting and clipping them. And then for physical models, we have to apply statistical bias correction and downscaling. And then for the ML models, we need to aggregate and resample it. And so there are multiple steps, and these are somewhat different for different forecast horizons, right? And for the ML models, of course, aggregation to HRUs and then to daily or hourly time steps is, of course, the most important part. And so before I close, I do want to highlight briefly that integration with other systems is, of course, also critical. We do not only want to serve our forecasts in our web platform, as nice as it is, but we can also integrate with APIs. So we do have an API for programmatic access to our data. We can also integrate with Kisters or do FTP uploads if that is something that you'd prefer. We can generate output for HECRAS, or we can integrate with the Fuse system as well. And then, of course, we do have a web platform, right? So with that, I'll just briefly summarize what I've talked about. The ML forecasts are based on LSTM model architectures that are trained on very large data sets, and they achieve pretty good or simulation skill. And then the forecasts are, of course, somewhat limited by the skill of the weather forecast. And they can do prediction in ungauged watersheds as well, which is really important. And on top of that, we've also added additional forecast endpoints for snow and soil moisture. We've added the capability to integrate real-time streamflow observations. And we've also deployed hourly short-range forecasts now. And larger streams are handled with a routing model. They're not handled by the ML models, as I've explained, but this is actually almost an advantage here. And as I've just discussed now, the forecast models, the ML models themselves are really not enough. This is probably not even halfway there. There's a lot of infrastructure you need to develop in order to do operational forecasting. That includes the actual forecast, but also the model spin up, right? And then also the entire data infrastructure and serving this as an API or a web platform. But this is actually work that Aquanty has already done. So with that, I can open the floor for questions. Thank you for your attention.